we have a surface bounded by a curve that is not necessarily contained in a plane, what the Stokes theorem says is that the integral of the vector field over that curve is the same thing that doing the double integral over the surface whose boundary is this curve, right? Over the surface of the curl of f ds. This is a more general version of the Green theorem. And the Green theorem, you have a region whose boundary is a curve, but all contained in the xy plane. In the Stokes theorem, this curve as well as the surface are all contained in R3 and doesn't have to be restricted to R2, to a plane. Though, in particular, if the curve happens to be contained in a plane, so then the Stokes theorem specialized to the Green theorem coincide in that case with the result of the Green theorem. Observe that we need, in order to calculate this double integral, we need to calculate the curl of the vector field. Observe that this integral that appeared in the Stokes theorem, this is the curl of the vector field, which is another vector field. So this integral here is a surface integral, like the ones that we just learned how to calculate. Let's calculate, for example, the integral of this vector field over the curve C, where the curve C is given by the intersection of this cylinder and the plane y plus z equals 2. So the intersection will be a curve like this, an ellipse here. So this is the curve where we want to calculate the integral of the vector field. And the vector field is given like this. So we could calculate this integral directly by the methods that we have learned before, but we can also calculate this integral by the Stokes theorem. So by doing that, we need first of all to calculate the curl of f. Remember that to calculate the curl of a vector field, one way to remember what goes in each component is to write down the determinant where jk, and here we put formally just the calculation of the derivatives, and then in the last row we put the actual vector field. In this case, so by doing this determinant, so eliminating this, we see that the first component is going to be the derivative respect to y of z squared minus the derivative respect to z of x. So by doing all these derivatives like this, we get that here is, in the first one is 0 minus 0, right, will be 0. For the second one, when we eliminate these two, we get the derivative respect to x of z squared, that is again 0, minus the derivative respect to z of this, that is also 0. So the second component will be 0. And the third one is going to be the derivative respect to x of x, which is 1, minus the derivative respect to y of minus y squared, that is going to be minus 2y. So then this is then the curl of f, the calculation of the curl of f. Just a reminder that the integral that we are trying to calculate to apply the Stokes theorem is the double integral over the surface of the curl that we just calculate ds. But what surface? There is no surface in this problem, right? There is just a curve, this ellipse that we draw before. This is the only thing that we have. So the point is that the Stokes theorem is valid with any surface, because any surface that we can have around whose boundary is this, a surface like this, a surface like this, any surface whose boundary is this will work. Well, let's choose the simplest one. Let's choose just this disk given by the plane there. So that will be the simple surface whose boundary is the curve that we are interested in. And so the surface that we are going to pick is going to be the surface just given by this plane, z equal to minus y. So in particular, in this case, rather than finding a parametrization, would be easier just to consider this as a function, right? Like the last method we see in the last lesson. So this is given as a function, g of xy equals 2 minus y. And so we just calculate here the derivatives, right? So the derivative of g respect to x, that in this case is 0, and the derivative of g respect to y, that in this case is negative 1. And we know that the domain where we are doing all this will be the part inside of the cylinder that is just given by the disk, right? X squared plus y squared less or equal than 1 in the interior of the disk. Okay, so having all this data, we will calculate the integral, the surface integral, with the formula that we already know. So that will be the integral over the domain, and so here we are going to write the components of this vector that are these ones, and so we are going to use also the partial derivatives. So we're going to get them minus 0 times 0 in this case, minus 0 times minus 1, and plus the last component here, which is 1 plus 2y. So this is the surface integral that we have to calculate. That all this, of course, is 0. So then the integral is just the integral of 1 to y dA. So in order to calculate this integral, since the domain is this disk, will be convenient to do a change of variables. So let's do a change to polar. So this is x equal r cosine, y equal r sine, and we are going to multiply by r, the differential. And so this is going to be equal to the integral between 0 and 1 of the integral between 0 and pi. So I'm using outside the r in this case, though it's the same, right? And so inside the angle. And so inside here, I'm going to substitute. This is 1 plus 2y, which is r sine. And then multiply by r. This is the integral between 0 and 1 of the integral between 0 and 2 pi of r plus 2r squared sine. So now we're going to integrate here respect to the angle. So this is the integral between 0 and 1, and the integration will be r theta plus 2r squared. The integration of sine is minus cosine. And this is going to be evaluate between 0 and 2 pi. This is going to be equal to the integral between 0 and 1, and now we evaluate this one at 2 pi. So we're going to get here and then evaluate it at 0, we will get cosine of 0, which is 1. We simplify this. This is 2 pi r minus 2r squared minus minus is plus 2r squared. And so this is just the integral between 0 and 1 of 2 pi r dr. Integrating this will be 2 pi r squared over 2 evaluated between 0 and 1. So the 2 cancel and evaluated at 1, this is just pi times 1. So the final answer is pi. So this is the calculation then of this integral by applying Stokes theorem.